I need to maybe
behaviors of these materials.
Sorry, Dr. Bartholomew, can you hear me?
No, unfortunately, no. Can next, please. Next. Thank you. So, if the first thing we know, or the first problem we need to face when we want to model masonry structures is to find out how the mechanical parameters we need to put into our model and to translate everything in number, the real behavior in numbers. So here I synthesize some laboratory tests we can perform to get these parameters. So, and here, starting from the left part of the slides, we have a compression test by which we can get the compressive strength of masonry, so the ultimate force the masonry can sustain in compression, the Young modulus, how it is deformable. In the central part, we have a bending. Finally, on the right part of the slide, we have what we call a diagonal compression test, which provides us the shear strength of the material, so the ultimate force the panel can sustain in shear. So these parameters are probably the most important ones we need to know, we need to assess for our design. And what I want to stress, all these parameters are macroscopic. What does it mean? They are not directly related, or they are related, but they are not representative of bricks and mortar. They are representative of masonries, right? So this is what we can say. This is important as a basic starting point to try to model masonry construction, masonry building. Next, please. Great. So now, if we move from the material itself to the building, we can recognize one important principle in masonry construction, which is called the box behavior. A masonry buildings shows a box behavior if all the walls are connected to each other, the horizontal diaphragms are well connected to the walls, and also the diaphragms are rigid, so that being able to transfer the inertial forces from the floor to the walls. So this is what we call with the one word box behavior. This picture on the left side is from your code, your regulation code, and does a great idea of what we want to explain. So all the buildings, if it shows a box behavior, all the buildings can contribute to sustain the seismic forces. And on the right part, this is an example of building showing a box behavior, since we have reinforced concrete rigid slabs. This is from my hometown, Catania in Italy, and this is 4-story buildings showing probably a box behavior during an earthquake. Next, please. Here are some pictures from your regulation, Nepalese guidelines, and some pictures showing typical examples of non-box behavior. So wherever we have timber floors, which are very deformable in shear and not connected with the walls, we cannot expect box behavior on the structure. Okay, so this is a typical example of a non-box behavior. It is also much more difficult to include in our models deformable floors. And here I reported a reference of the New Zealand code providing some guidelines, some suggestions about this. But in this case, the model of the entire building is something much more complex. Next, please. So when the building doesn't show a box behavior, what happened basically is that we can observe local failure mechanisms. These failure mechanisms are mainly in out of plane. So they are orthogonal to the walls and they produce the failure, the rocking out of plane failure of some walls. We call them local because generally when they happen, the remain part of the structure could be undamaged, but part of this completed failure. If the wall collapsing in out of plane is also a wall supporting a floor, we can have then the failure mechanism could move from local to global. But many times, as you can see in this picture, a wall is completely failed, the other part of the building is there. These pictures are from the Messina's earthquake, 1908, and L'Aquila earthquake, 2009, both in Italy. So this is they are the out of plane. So please, can you go ahead to see the rest of the slide? So this, yeah. Oh, okay, sorry. So these failures are the most dangerous ones. And then strongly in retrofitting techniques, we need to avoid, first of all the out of plane failure mechanisms. We can go next. Okay, already said. Next slide. Right. If and only if we prevent the out of plane failure mechanisms, then each wall can sustain the seismic actions in plane. And then we can have main three failure mechanisms: flexural mechanism, diagonal shear, and the sliding shear behavior. And here some pictures showing the typical cracks that I think you are most familiar with since they are observed after any strong earthquake, including here in Nepal. Next, please. Different mechanism. This seems means different behaviors also in terms of energy dissipation. Here we can see some experimental tests in which you can see, for instance, the diagonal shear failure is much more dissipative since we have the area included into the loops is higher. So this is something to bear in mind. Depending on the mechanism my model could predict, I can expect more or less energy dissipation. Next, please. Now let's move a little bit more into the numerical world, the numerical simulations. So if we want to simulate the out of plane mechanisms, the most effective method used is the limit analysis. Basically, this analysis consists in imposing an ultimate equilibrium and to evaluate the maximum lateral force that produces the rocking of the wall. It's very simple because it doesn't require many mechanical parameters, but very effective. We can move. Next. Okay, I will not include other comments because I need to go a little bit faster. But let's say it's important to mention limit analysis in this regard for out of plane failure mechanisms. Next, please. Here, just an historic details. Probably the first one, who proposed the use of limit analysis for structural assessment of masonry buildings is from Italy, Professor Giuffre in 1990s. This is can you click? This is a book, unfortunately in Italian, but very interesting relating to this aspect. Next, please. Oh, you can switch again and then to see. Oh, no. Okay, just another click to have all the slides so I can comment everything. Right. So if we move from the out-of-plane behavior, local mechanism, to the global behavior of the building, so now we are interested to capture the behavior of the entire buildings, the problem becomes a little bit more complex. We need to model all the elements, all the walls, including the diaphragms. And we have two choices, basically. One is to use the FEM, finite element approach. It's very general, very powerful, and is reported in the slides on the left part of the left part of the slide, and consists in discretize or brick by brick. And in this case, we call them mesoscale models, or in the right part of the slide, using the so-called macro scale representation, finite element representation. A little bit more, let's say, less computational demanding, the macro scale discretization, since we lose the information about where each brick is, and we homogenize the behavior of the masonry. So we are accepting a great simplification, but the reward is the reducing the computational time. However, even less than the macro scale, the mesoscale discretization, this kind of model are quite consuming in terms of computational demanding. This is why, next please, some research has been focusing even simplified more the problem. And then in this case, the aim is to replace each element of the wall, in particular each pier between two, the part of masonry between two openings, and each spandrel between two openings aligned to different stories in one or very few elements. This is the so-called equivalent frame model, and each panel is replaced with a column or a beam. Importantly, the part connecting beams and columns are supposed to be rigid. This is probably, next please, the main limit of this model, which sometimes we observe damage also in the connecting part. This is why, starting from 2004, something like that, at the University of Catania, next please, we developed another model, and we called it the discrete macro element model, trying to move from the 1D discretization used in the equivalent framing model to a more consistent, geometrically consistent simulations of each panel, and in particular also simulating the region connecting piers and spandrels. Next, please. I will go a little bit faster describing. I have a couple of slides describing this model, but I want to reduce the time, so I will go through a few details, but not. Okay, just to give an idea about how this model works. So each panel is basically replaced with an articulated quadrilateral, which is very easy to understand, is deformable only in shear. So it means that the flexural deformability is not included in the model itself, but is replaced into what we call the interface elements, which are the distribution of links, discrete links. This is also why the model is called the discrete model. And these links, along with the edges of the element, have to regulate the axial behavior of the masonry, plus eventually the sliding between the two elements. Next, please. I will skip totally this one, and I go to this, which is quite important. So even the model is very, very simple in terms of mechanical scheme. We can recognize it can simulate in the three-failed mechanism we presented above, using the different links we introduced. This is quite useful for the assessment, because as we said above, depending on which failure mechanism is activated, then we can be much more or less confident that the structure can dissipate energy. And this is, for this reason, it's important to have a model which is able to give us this information, which is the failure mechanism that is activated. Again, next, please. I will skip this one as well. And of course, we do a lot of, and we accept a lot of hypotheses, some of them quite strong. So in any case, each model should be validated. And in the, let's say, many times, the best validation is again experimental test. This is basically what is represented in this slide. And what when we evaluate the reliability of a model, we need to understand how he predict the force, the level of force, and deformability of the real masonry. This is what is represented in the left part of the slide, but also how the model predict the failure mechanism. This is sometimes is this information is the value of this information is underestimated. How the model produce predict the failure mechanism, but this is fundamental. So this is what is reported in the right part of the slide. Please again. So next. I will skip this. Sorry, but I'm trying to reduce the time. So I'm skipping just what I don't need to for the be understood during the this presentation. So the model, as I presented above, is able just to simulate the in-plane behavior of masonry. And this is good when the structure shows a box behavior. When it is untrue, when the out-of-plane failure mechanism can happen, can be activated, we need something more. We need a model able to simulate also the out-of-plane behavior. This is what we did, enriching the model, the discrete model, from a 2D to 3D model, 3D kinematics. And the only aspect that I want to remark here is that what we had in terms of interface elements, so the discretization of the link along with the edge, now is replaced with the number of rows of links in parallel in order to simulate the flexural behavior in each plane of the masonry. And this model, now we can 5. Oh, right. So, and we used this model to simulate the out of plane behavior. So we can go next just to show the slides. Skip this is the validation, but we can skip. And what I want to show you is this is the kind of output we can obtain when the model is able to reproduce the 3D behavior. The failure mechanism is not in plane or out of plane. In this case, it can be combined in plane. This is the simulation of a church in which, of course, the out of plane behavior is fundamental. Okay, we can go because we have 5 minutes. So I can spend these 5 minutes to try to deliver the final message I want to transfer today. So which kind of analysis can we do when we have this kind of model? So a model able to follow the nonlinear behavior, the damage through of the analysis. So several analyses can be performed, even dynamic, and which are the most, let's say, accurate, since the earthquake is a dynamic phenomenon. However, in order to simplify the analysis and in order to require less parameters, equivalent static analysis that we call pushover analysis are at this particular historic moment the most diffused method of analysis in seismic engineering. And in what does they consist this kind of analysis? Basically, the earthquake is replaced with the distribution of lateral forces. We can consider a different shape of load. Here is represented one proportional to the mass, one proportional to the mass and the height, but this is not the key aspect. The key aspect is that the earthquake is simplified as horizontal forces, and the main information we get is reported on the right part of the slide. We will get the capacity curve of the structure, which is the displacement of a control point, generally at the top of the building, against the base shear so the total force we are applying report on the y-axis. This graph, the capacity curve, is what we need to assess our structure. And I'm going to go to the final part. So starting from the capacity curve, you can switch again. Okay. So the capacity curve is our starting point for the assessment, for the structural assessment. And basically, what we do following a specific code or specific guidelines, we identify what we call the performance levels. So specific point of the structure on this capacity curve. If we follow Eurocode, and this is the case representing my slide, we can define the 3 performance level. Going through, starting from the right to the left, we have the near collapse performance level, basically where the structure is very close to the failure. The significant damage performance level when the safety of people is compromised. And finally, the damage limitation performance level when the damage of the structure is activated. So this is what we need to assess our structure, to identify these points along with the capacity curve. Can we move to the next one? Next slide. Okay. Here, let's click again. Right. So just want to remark one thing. Right now, we said that performance levels are defined along with the capacity curve. This is what we call the global performance level. However, new research and new regulation are trying also to define the performance level of the structure, looking not only at the global level, not only at the capacity curves, but looking at each part of the wall, like some criteria are specified in terms of lateral drift. So the formation of a specific story of the wall, or even click. Next click, please. Or even looking at a specific element of the wall, each pier of each spandler. So why I think it's important to remark these aspects. So when the regulations that I'm following ask me to monitor a specific element, a specific pier of the wall to go through my assessment, the fact the using of a macro element discretization as the one we saw, the discrete macro element of the equivalent frame model, could be very, very helpful. Because if I use a finite element method, I will receive a local information. Each point of the masonry, I will receive a local information. With the macro element approach, I receive a global information about each element of the wall. So I can look easily what happened at each pier, each spandler, and then I can identify if I reached any performance level of the structure. And okay, I think I conclude because the next slide, then I want also to speak about the performance level are the capacity of the structure at each capacity at each level. Then we need to compare with the seismic demand. I will leave this because I don't have time. Basically here, what we do, the basic assumption is to again, using the capacity curve, which is the most important thing we have to look when we use a pushover analysis, we define a sort of equivalent. We call it a single degree of freedom. So we replace the big structure we are modeling with the system which has just one independent displacement to be described. Then we can use spectra, design spectra to easily go through the evaluation of the demand. So the assessment will be performed comparing displacement demand with the displacement capacity. This is a completely different approach that maybe many of us are confident with. So comparing forces. Here we compare displacement. And this is the main differences when we use a pushover analysis. I think we can go through the conclusions. And then what I want to highlight is the behavior of the masonry structure. And here the most important thing is the distinguish between out-of-plane local and in-plane global behavior. And the particular typology of macro element strategies for modeling coupled with pushover analysis to have relatively easy, but reliable assessment of the structures. Thank you very much for attending this presentation. I hope I was not very late.
Thank you, Dr. Panto, for guiding us through the whole modeling approaches in masonry. He talked about micromodeling, simplified micromodeling, and then came to macro element modeling as well, in which we have basically two categories, which he talked about equivalent frame method and his own model that he developed with Professor Kallio, 3D macro element method. So I think the best part about the 3D macro element method is its ability to capture the outer plane mechanism in addition to in-plane failure mechanism that can be done also with EFM. So thank you again. Now, sorry, we had a little bit of technical problem. So we hope that the session will be very smooth now. Moving forward, our next topic is a damage study of brick masonry buildings in Kathmandu Valley post 2015 Gorkha earthquake. This will be presented by Dr. Rajan Sual. Dr. Sual is a well-known name here, and he's a current president of CNEP, associate professor at Woodstock Engineering Campus. He has been teaching several subjects for a long time. I would like to invite Dr. Sual on stage to share his valuable research.
Bharat, sorry for disturbance. Damage study of brick masonry building in the Gorkha earthquake 2015. Actually, we can study the 2-3 methods. One is the analytically, which is being studied since long back. That is the one method. And another method, and what it was happen in the earthquake. What was the damage pattern in the different type of the masonry buildings? Generally, in this work, I focus in the brick masonry, mainly in the two part. One is the palace type of the building, that means darbar, and another is the residence type of the building. Without delay, please next, please. These are the different earthquake histories. Next, please. Next, please. And next, please. And this is basically in the Gorkha earthquake, and there is a more than 138,000 buildings were damaged, and partially damaged 122,000 almost, and collapsed 10,000, more than 10,000, partially damaged 13,000, and it was recorded around 9,000 people's dead. And please next. Next, please. And basically, this type of the masonry buildings in the Kathmandu Valley, when we are taking the brick masonry in the mud mortars mostly, and the study of this part is the very important in the earthquake, and because we should know how the buildings were damaged and collapsed or cracked in the earthquake. Next, please. And this is objective as we discussed. This is what was the damage in the different type of the earthquake, which type of the damage occurred there, and what is the possibility, what might be the possible causes of these damage. Next, please. And now let us discuss about the palace type of the building. Next, please. And we can see this is a Pulso campus building, another Niketan, and here out of plane failure. In this case, it is the right part of the top. This wall is moved to the right directions, and similarly there is another also. Please next. And here in Bhaktapur, in the Sri Padma High School, and we can see the out of plane failure of this top floor, and Darbar High School, and it is already reconstructed. And here also, whole this part of the wall came out from the plane. Next, please. And Basantapur Darbar Square, you can see the whole wall came out, and it was collapsed. And Gaddi Baitak also, you can see this part. Next, please. And in the Bhaktapur, and you can see that this is the National Art Museum, and almost it is already in the tilted, and it is in the certain sway and certain deformation from the vertical plane. And now you can see this type of the deformation even nowadays. Next, please. Out of plane. And here is in the this is in the same in the Bhaktapur for the next building. Next, please. And this is the Patan Museum, and this is also the one of the example of out of plane failure. Next, please. And causes of out of plane. This is just assumption and the discussion. And even though thickness of walls are 600 to 900 in the ground floor, and top floors 400 to 6 floor, and the drifts is increasing in each earthquake. And the basic causes of this failure is there is a transverse walls are not properly connected in the main wall and it is detached. That is the one thing. Another is the transverse walls are distance are much more than the required. Next, please. And we can see in the top floor nearby the roof there were not a connection, and most of the in the outer part of the corridor, for example in the that is the Rani Pokhari, that in front of the Rani Pokhari Darbar High School, the whole one wall collapsed, out of collapsed. Next, please. And this is in the Shital Nivas. You can see in the different failure in the inside the building. Next. And this is the internal wall failure of the same Darbar Palace. Next. Basic causes of internal wall failure is thickness of internal wall with respect to the length and breadth is a much more slender. Means it cannot resist the lateral force enough. And another thing is the openings in most of the internal wall, in most of the cases of the internal walls, there are big openings, and due to these big openings, and the internal wall fail. Next, please. And vertical and inclined shear failure. We can see the vertical failure here. Next, please. And this is in the Juddha Palace building in Tinchuli. We can see the vertical failure here, vertical shear failure, because the two openings are very close and the distance between that one is not enough. That's why that it cannot resist the vertical shear in this part. That's why we can see the cracks there. Next, please. And here is also, and next, please. And the basic causes of this one is in the palaces, the vertical failure at the incline failure is the huge openings between the two floors, and between that it is not enough the timber band, and some of the structure there is no timber bands, and some are there, but it is seen that that might not be enough, and no little and shield bands also. Next, please. And you can see Sri Padma High School here, horizontal and inclined shear failure. These all of the columns are fail. Even in the Gaddi Baitak, this is all columns are failed because it is very slender. It is the very slender. It is required to the little bit bigger size. Due to this slenderness, and we can see the cracks and some of the columns and some of the parts fail. Next, please. Next, please. Slenderness of column is the more. This is one of the cause. And slenderness big column is huge opening are very weak in earthquake. Where there are big openings in the brick masonry, horizontal stiffness is drastically decreased, and this is the one of the causes of failure. Next, please. And this is a Darbar High School, and after earthquake, when I visited there is a full crack in this part because due to there are two stiffness. One is the small one type of stiffness, another is the another type of the stiffness. Time period is different. That's why in the junction of these two, even the one structure, and we can see the huge cracks and failure there. Next, please. And this is the different causes because mainly in the corners and when there are connections of the one buildings for two parts, and in the earthquake in the different direction, and due to the this stiffness, different stiffness time periods are different and it moves in different way. That's why we can see that this type of failure in the most of the Darbar areas also. And here arch failure in the Kesar Mahal, and we can see the arch failure here. And it is seen that in top of the arch, one is that is the deteriorating, that is the one of the cause. Another is the arch between the floor, that is the top floor, and the bottom is the less. That's why due to the less stiffness, we can see the failure in this part. Please next. Here also we can see the falling of the arch part. Next, please. And this is the causes of failure. Please next. And we can see here failure in the joint because in the joint. This is constructed in one time and it is renovated in the later times, and the bonding between these two parts are not good. That's why it fell. Next, please. And this is the again next. And most of the cases in the Darbar buildings, and there is a dilamination of roof and the walls, and water is continuously leaking there. Due to it, the material is decaying, and the properties of material and strength is decreasing. Because of it, it cannot resist the enough strength. Next, please. And I will not go in detail. This is please next, 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 and next. Please next, next. And the brick masonry building in residence type. Next, please go. Next, please. We can see diagonal here. This is the residence buildings. Previous was the palace type of the building. This is a residence building brick in the mortar in the Kathmandu Valley, how it fails. And we can see the diagonal failure here, diagonal cracks. Next, outer plane failure and diagonal cracks here also. Here also. Next. And we can see the corner failures of the buildings. And next, please. And corner type of the failure, because they are not connected properly with the two wall, were not connected properly, and when they were constructed in the not in the same times, and no timber connections and other types of the connections and no bands. That's why this corner fell. Next, please. And vertical crack also, again, same problem. And it is this there is the construction of this part and the connection between the two bricks are not proper way, and they are almost in the same line vertically, and we can see the failure. Next, please. And here vertical cracks at the corners. Next, please. And this is the outer plane. We can see the outer plane failure there when there is not properly connected with the roof, and the transverse walls are not properly connected with the main wall, and we can see this outer type of the failure mostly. Next, please. And outer plane whole wall failed here also. Next, please. And in the most of the cases in the roof, this gable type of the wall were not properly connected in the roof, and there is no bands, and because of it, due to the inertia of force, and it could not retain with the main structure, and it fell. Next, please. And we can see here also same in the Bhaktapur failure. Next. And another failure, whatever we could see in the Gorkha earthquake, in the masonry, brick masonry in the mortar, and two layers were not connected in proper way. This is problem where in the Jadar court also, and we have seen and we have discussed so many few times also. They were not properly connected, and the one single blocks are not there, or connected blocks are were not there. Because of it, due to the earthquake, outer layer fall, even though inner layers are there. And next, please. We can see here it is fallen to the outer layer only, not because that is no connection between the inner and outer layer. Next, please. And mainly this conclusion and recommendation, mainly in the residence style. Diagonal cracks have been observed most of the buildings due to the absence of whole bands, lintel bands, and shield bands are like that, and lack of connection between the perpendicular walls, and because of it, it fails. Next. And rigid diaphragm, because due to the weak diaphragm between the wall, with connection between the wall and the that is a floor diaphragm, and because of it, and it could not rigidly connect it with the wall, and in where there is a good connection, it's no problem. When there is no proper connection, it fails. Lack of gable bands, due to it, most of the roof walls, gable walls were failed due to the enough rigidity, this portion with the roof and the other part. Next, please. Next. And we can see the another things also. This masonry wall or buildings were has a lot of age, almost 180 years, 100 years, and more than that one. Because of it, these materials became already weak, and there in different earthquake, and it faced a lot of earthquake, number of earthquake. Due to it, the bricks and mortars were shaken so many times, and we can see the micro cracks there. Even though we cannot see the micro cracks, but in the earthquake it fell, because even in the 1990 earthquake, same buildings which were in the Bhaktapur, it did not collapse. But in the recent earthquake 2015, most of the buildings, same buildings, were collapsed. This is the due to the age of the building and deterioration of material, and that is a time factor. Okay, next, I think it is finished, and thank you very much. Certainly, this is the observation, because we are talking about the brick masonry with mud mortar and cement mortar, mainly in the mud mortar. In the earthquake, how this type of the brick masonry in the mud mortar failed, and it can be validated later in by numerically and in the model, and we can suggest mathematically how what should be done later. But from the engineering judgment also, we can suggest this type of failure where because of it, and we can suggest to in the future generation and future construction what should be improved in this building. And thank you very much.
Thank you, Dr. Suwal, for a very interesting presentation and shining light on the vulnerabilities of our local architecture. Definitely, Gorkha earthquake 2015 was a unfortunate event for all of us, but it was also a great opportunity to learn for structural engineers like us. There were different kinds of failures, as already mentioned by Dr. Suwals. So now, as we delve into the depth of this program, it is time to explore the role of innovative materials in seismic protection. I would now like to invite Dr. Stefan Sinewski from Durham University to take us through the fascinating world of nature-inspired composite materials, research frontiers, and future applications in seismic protection. Dr. Stefan, the stage is yours.
Next slide. I need that pointer as well. No. Oh no. Sorry. I just okay. Thank you for the nice introduction. I think this is a nice circle actually for me, because my PhD was on energy flow in progressive collapse of steel frame structures. It was funded by. Okay. Okay. So go to that side. Okay. So I'll stand here, so I'm visible in the camera. And basically, the topic I want to present to you is maybe the discussion or thought-provoking presentation of what we can learn, what can we learn from nature. So next slide, please. Next slide. Okay, next slide. Okay, so next two slides will be about natural structures that we take for granted. Next slide, please. So one example is this abalone shell, nacre of abalone shell. We look at the shells and we don't think much of it. But if you look closely at the shells, they actually are made of tiles and they resemble brick and mortar structures, which is not obvious when you look at the shell. But when you look closely at those tiles, they are made of relatively weak materials because they are kind of organic mineral materials. But when you analyze the assembly, the shell, it is free the fracture toughness is 3,000 higher than of individual bricks. So it's a very tough structure developed by nature over millions of years for self-protection, right? So nature was experimenting, evolving, and arrived to this structure. So I want to talk about this structure a bit. So it's made of those tiles, but the tiles are interlaid with organic matrix, which is made of fibers. So it's a fibrous porous structure, quite flexible. And the initial assumption when this was studied mostly by groups in the United States, in California, that the reason for those soft interfaces is to deflect cracks. So basically you drive the crack into soft space and you extend the surface of the cracks and then more energy is dissipated. So it doesn't crack like glass, but the way it cracks is more like a windshield in a car when it kind of, cracks everywhere. It's a distributed cracking. So that requires more energy. Next slide, please. Another interesting example, which again, I will talk more about this, is this hierarchical structure of a grapefruit peel. So again, we eat fruits, we chuck the peel into the bin, we don't think much of it. But if you analyze it closely, the one interesting thing is the levels of hierarchy. So in structural engineering, maybe we have 3 or 4 levels of hierarchy: building, wall, and maybe bricks and mortar. But if you look at nature, there is the fruit, there is the peel, and the peel has an important function. So when the fruit falls and it hits the ground, it needs to remain its integrity. If it fractures or cracks, then microbes and bacteria and fungi get into the fruit and then they affect the seeds. So this is essential for survival of the fruit, to have this toughness of the skin. And how is it made? So if you look closely, it's a porous material. The porous material is like a lattice structure, and the lattice structure is made of tubes, and each tube is made of composite material. And this happens at different length scales, and those length scales interact one with another. And that's how the system becomes the most efficient. So the reason I talk about this is because the way the material is made of, the way the mortar is made of, it interacts with how the building behaves. It's not disconnected. All those things, they interact. All those length scales, they are linked to each other. Okay. So here I want to entertain you maybe for 1 or 2 minutes about a project that I had in the past on non-cuttable material and how nature, inspiration from nature was useful to solve this problem. So there was a request from the, next slide please, from the security agency in the UK to create material which cannot be easily cut with angle grinders, because that is a security threat. It's very cheap to buy, and you can get into power plants, water pumping stations, and cause damage, which is happening around the world now. So what is the solution? One solution is, let's go for the hard material, hardened steel, maybe diamonds, ceramics, very expensive, right? But why not learn from nature? So one option would be to say, why don't we merge this grapefruit peel with the shell structure? So why don't we use the porous metallic foam with ceramic inserts? And why don't we, next slide, please. So this is how it's made. So this is not that interesting. It's basically like baking a cake, but you use metallic powder, not flour, and you put it in the oven and it rises like a loaf of bread, but it's a metallic bread with kind of metallic foaming agent. Next slide, please. Mechanically, the material is not very impressive. It's a crushable porous aluminum. So 10 megapascals, it's comparable to, porous concrete. So it's not really hard or tough in that sense. Next slide, please. Next slide. But this is what happens when you try to cut it. Okay, the disk disappeared, right? And how did it happen? I mean, we all know you can cut blocks of concrete with no problem, right? So this is a relatively soft material. So what is making it so difficult to cut? Next slide, please. So this is the principle. So the principle is that we basically leverage vibrations. When you try to cut it, there is an internal resonance between the spheres and the cutting blade, and this creates very high strain rate loads at the interface, and these vibrational loads destroy the blade. So basically, this is an example, next slide, please, where we can be smart. We don't have to use brute force, strength or heavy solutions. If we are smart, like nature is, and we can arrange structures in a hierarchical way, we can achieve the required outcomes without really spending a lot of money. Next slide, please. So here I want to talk about the current project I have with my student Anna Wedderburn and a number of other colleagues, which is basically how can we learn from nature and produce 3D woven composites? And this will be related to mortars and fibers. This will become clear quite quickly. Next slide, please. So what are woven composites? I'm sure you are aware of those. These are effectively technical textiles which are impregnated infused with resin, and there are different techniques of achieving this. Next slide, next click, please. Can we click next, please? So I wanted to show this kind of bag made of jute because it is also a technical textile. It's not a garment. It has its function. It's probably not expensive. And maybe we can make some use of those fabrics to reinforce the buildings against earthquakes or maybe mortars and so on. So this is where I'm going with this talk. Next slide, please. So I will go back to this structure of the abalone nacre. So it is made of rigid tiles interlaced with soft fibrous material. Next slide, please. So the idea we explored in this project was what happens if we introduce soft yarns made of polypropylene that to mimic this mortar and brick structure. There is soft interlaying material embedded in a rigid composite. How is it going to affect the fracture of the material? Next slide, please. To basically mimic this toughness of the shell. Can we have the same effect in a 3D woven composite? Because toughness is a problem when it comes to composite, especially under impact. So this is a CT scan of the small sample that we performed with our colleagues in Durham, with Alexandros and Maria. So we can see the kind of yarns. And interestingly, each yarn is made of 6 to 12,000 fibers, which are nanoscale size. So that's one length scale. Yarn is another length scale. Then you have resin and the yarn, another length scale. This becomes a panel. So now we are in the maybe 5 levels of hierarchy with those materials. That's why they're so efficient. Next slide, please. So here I want to show you the initial results. So you can see this is can we click, not the next slide, but just click through the animations here. So you can see this is a drop kind of impact. So it goes down. Let's click again. And this will hit the sample, which is here, and will break it. So let's keep clicking. These are the stress waves that will propagate outwards after the impact. Click, and we can analyze those samples using the CT scanner. Next slide, please. So you can see the samples are quite small. This is like a small coin, and there are multiple layers of yarns. Next slide, please. So this is a CT scan. So let's click through the slide. If you click pause button, I think let's go back. That was too quick. Go back. This one. So you see, we are scanning the plane at the fixed end. So there is no failure there. Here the sample ruptured. It was a composite sample that broke into 2 parts. And when we look at the cross section, we can see the yarns and resin, but no cracking, right? Let's go to the next slide. And yes, so here we move the plane. This is the blue plane. You can already see there are some cracks in the composite. So the visible damage is here. It broke into 2 parts. But when you look at the CT scanner, there are micro cracks, which are inside the material. Next slide, please. And click pause so we see the section. So here we are close to the damage section. And you can see there is even more micro cracking there. So that's the interesting feature of damage, that there is like a visible rupture, but there is also a lot of invisible kind of planes. And if we can manage this and design this in a hierarchical way, maybe we can dissipate a lot of energy. Maybe we can create like a windshield kind of distributed. That would be the holy grail, as opposed to the situation when there are 2 or 3 discrete cracks, because then the energy is not dissipated. It's like a very brittle fracture. Next slide. So this is a comparison of this conventional carbon that I was showing you that breaks into 2 parts. But now when we introduce the polypropylene kind of soft yarns that I showed you before, there is no rupture anymore. Like the 2 parts remain connected after the impact. Next slide. This is like the close-up view. You can see the fibers, the polypropylene yarn are still there. Next slide, please. And this is a qualitative, again, these are early results, but you can see that this is the pure carbon, and this is the carbon sample with soft yarns, polypropylene. And polypropylene is effectively a material you can source from recycled bottles or plastic. So this is not an expensive material. You can see there is improved fracture toughness, not by much, maybe by 20% or less, but it shows that in principle, this mechanism could be useful even in those advanced composites that you use to build aircraft or performance objects. Next slide, please. So where are we going with this next? We are going to basically click pause. So yes, so our effort is mostly focused on computational work at this length scale of yarns and fracture and interfaces, because we want to optimize the material. So nature optimized the material through evolution, millions of cycles, millions of years, some species go extinct and so on. We can try to optimize the structures using simulations. So basically maybe trial and error, or just search what is possible, what is happening, and maybe we can encounter a good design and then use it and manufacture it. Next slide. Next slide. So I want to go back to this abalone shell. So again, it's a brick and mortar structure in a way. So there's this soft inter tile layer. And please click pause so we see the other graphic here. Interestingly, this matrix is made of porous fibrous material. So it seems that evolution suggests that fibers should be used in the mortar, some kind of fibrous structure, maybe also slightly porous. This is something that nature kind of favored in the natural beings. Next slide. So these are kind of proof of concepts that tests that were performed with sisal fibers, which are common in Brazil, but jute could be used as well, by Emily Martin, the supervision of Dr. Panto. So let's click next. So if you see there are no fibers, it's just tails. There's one rupture plane. But if we see more samples, so let's click any button, so you can see the images there. You can see if we add 1% fibers or 2% fibers, and even we look at the close-up view, you can see that it becomes more of a ductile kind of behavior, and it doesn't break into 2 or 3 discrete segments. Next slide, please. Next slide. So but I wanted to highlight something that maybe is overlooked, and I think it was mentioned by Bartolomeo and others. If you analyze those natural structures, they also have quite intricate interfaces. So it's not only the fibers in between the bricks, but the interfaces are not smooth. They have some interlocking mechanisms, and this interlocking mechanism, they were shown to contribute to the in-plane fracture toughness. And I know that after me, there will be an invited talk by sponsor, Brick Factory. So I think there is also potentially some work to be considered on those interfaces. Is there a potential for some interlocking? And what is the interface between mortar and the bricks? And interestingly, in the natural structures, those length scales are very small. So here they are nanoscale, because nanoscale length scales are much stronger. So maybe this also needs to be carefully considered. What is this interface? What length scale is relevant? And maybe this can be engineered as well. Next slide, please. So again, this is a close-up view of this interface. And next click, please. Yes. So you can see when those things are shifted, they interlock. And to break those small segments, it dissipates energy. And it improves the resilience of the system. Next slide, please. So this is the microscopic view of this terrace growth. This comes from a work by Professor Meyer's group. I want to acknowledge this. This is not our work that was done in California. So I'm just showing you those images. You can see the length scales microns, and these are the kind of protruding interfaces. I want to also qualify, or maybe add, I would say, a caveat statement to this discussion is that nature has more functions than structural. So this is growth. So those layers grow, and there is also fluid transport and so on. So some of those shapes may be for other functions, like growth, for example, and so on. So maybe this is not always relevant for us, unless we want to grow buildings. Maybe there is a way to have a growing mortar that would grow or regenerate itself, but maybe that sounds like science fiction now. So let's go to the next slide. So this is like a quick summary. I try to keep to time. I think I'm nearly finished. So the future work in terms of our group, and this is funded by UK sponsors, is for those fiber hybrid composites and to develop computational models and optimize the design. But we have been working with Bartolomeo together on basically translating some of those models or findings into kind of brick and mortar structures using natural fibers like jute and CT scanning capabilities that we have and analysis to basically create, I would say, ductile failure in those mortars and understand what is important, what fibers, what lengths, what properties to make the best of what we have. Next slide. So in conclusion, nature uses soft interfaces to increase the crack area, to increase the fracture toughness. There is some kind of active management of fracture propagation, preferably to create the largest area of cracking. Modeling and characterization are essential, or maybe experimental search is also okay, but we need to find what is the best configuration. And interestingly, all those length scales interact. So maybe for different types of buildings, different fibers should be used, or different thickness of the render. It's not that the one solution will work in every system, because if you look at natural organisms, they all have different architectures. Patterns at interfaces are quite important. I will go to the previous slide just for the last statement. So I want to also mention this. Can we go please to the previous slide? And it seems that these renders or mortars with natural fibers, it seems that the studies of natural organisms indicate that this should be studied and investigated. And we may find an interesting outcome that will improve safety of buildings. And potentially this solution it is not expensive and maybe not difficult to achieve. Like it is maybe a low-hanging fruit. And the other aspect I like about this is that renders can be easily replaced after each earthquake. Or they are easy to, if they crack and it's like a windshield in a car that is completely micro-cracked, you can just replace it with a new one. It's not a major intervention. So it effectively could become like an energy fuse. But again, I don't make a statement that this is a proven solution. We definitely need to explore it and find out for sure if it works or not. So this is the last slide. The next slide, please. Thank you for your attention. And thank you. I try to be fast. Yes.
Sorry. Thank you, Dr. Stefan. That was really interesting. Also, thank you for offering a glimpse of innovative approaches that can redefine our future construction methodologies. I would also like to thank you and Dr. Rajan Suwal again to manage your time very effectively and pulling back us on track again. So we are on time now. It's a good thing for us so that we'll run our other sessions very smoothly. So before moving ahead now, it's now time to appreciate our sponsors. We have two sponsors today, Barahi Bricks, famously known as Hira Bricks also, and the Venus Construction, who is working a lot in rehabilitation works. So let us have a small video presentation from Hira Bricks first. I'd like to iterate again that Hira Bricks has significant roles in our heritage conservation, protection. They have been supplying our traditional bricks from long time, and it is truly a matter of pride to have them as our sponsors. So before moving to our next sponsors, I would like to again remind all our participants, if you have any queries, please note it down. We will collect it during the tea break session that is following very soon. So now next we have our next sponsor, Venus Construction. Venus Construction is actively working in rehabilitation works from long time, and we have Mr. Anil Katyal.
Consolidating materials which can give the more durability to your masonry, because water increase can hinder your
It's time for a tea break, but before moving to the tea break, I would also like to request again to hand over all your queries so that we can organize it and discuss at the end. And
Hear me? Buongiorno. Thank you for your presentation. It's an honor for me to participate to this very important conference, and I have to thank all the organizers, and I have to thank the group of Nepal for organizing within the University of Durham this very nice, important conference.
Okay.
So,
Professor Kalio, are you ready for your presentation already?
yeah, I'm ready. Now I have to share my screen.
Let us wait maybe for a minute. We are expecting all our participants to be in. I see almost full already, but you may be already preparing for your slides.
Okay, thank you.
Professor Kalio, you may start your presentation now.
Thank you very much. So the title of my presentation is Numerical Modeling of Retrofitted Masonry Buildings. And this is a companion presentation with the presentation that already done previously, Professor Pantò. And just a moment. Okay. The main causes of structural failure for masonry structures are related to different causes, like maintenance, earthquakes, time-dependent deformation effects like creep phenomena, flooding and settlement, and human actions like war, terrorism, or structural alteration made by humans, and also fire. It's important to emphasize that with just one word, masonry, we refer to an heterogeneous and anisotropic material that is obtained through the assemblage of units and mortars. And the result of this assemblage is very different from the structural behavior of each components. And with the single word masonry, we refer to a great variety of masonry typology with very high differences in terms of stiffness, strength, ductility, and cyclic and static and dynamic responses according to the specific masonry considered. The detailed modeling of masonry, as already Professor Pantò illustrated, is practically impossible to model from practitioner, considering the detailed modeling of the components. So an homogenized approach is generally considered. So the masonry is modeled as an homogenized media with isotropic or rarely orthotropic nonlinear properties according to specific inelastic laws. And the effects of structural retrofitting are generally considered by modifying the constitutive laws for the homogenized media, or in some cases, considering a detailed modeling of the reinforcement. The main issues in modeling the nonlinear behavior of masonry structures with or without a retrofitting are mainly related to the difficulties to characterize the masonry material. And in presence of retrofitting measures, these difficulties is further complicated by the need to consider the interaction with local or spread retrofitting solution. The high heterogeneous nature makes very difficult to determine deterministic mechanical properties. And so the results have to be considered in average way. The values of strength and low ductility may vary in an extremely wide range according to the masonry typology, and are also strongly affected by the choice of the adopted retrofitting solution. Cyclic and dynamic response are very difficult to not only to model, but also to experimentally evaluate. And few experimental tests have demonstrated that according to the masonry topology, very different constitutive law can occur with different strength and ductility, and with different degradation according to the specific masonry typology considered. As Professor Pantò already presented, in 2003, a discrete macro element was introduced, and it was introduced with the undergraduate thesis of Professor Pantò. The first model has been introduced by considering a plain discrete macro element to model the behavior of masonry wall according to a geometrically consistent model. Then in the PhD thesis of Professor Plantot, the model has been extended to include both in-plane and out-of-plane behavior. And this was the first macro element that included both the in-plane and the out-plane macro element behavior according to a simplified approach. This model has been implemented in a software that is called the ISTRA, Historical Structure Analysis, and has been used to model the in-plane and out-plane behavior of entire buildings like the church presented in the slide. Successively in 2011, another PhD thesis of Professor Carnizzaro extended this macro element approach to the curved geometry in order to account also for domes, arches, and curved geometry element inside the historical masonry buildings. The philosophy adopted for the curved geometric macro element was exactly the same that was previously adopted. So each element possesses only 7 degrees of freedom. 1 degree of freedom is related to the shear deformability in a main plane of the element, and the other degree of freedom are related to the rigid body motion of the element. And the interaction with the other elements are lumped in the nonlinear interfaces that rules the membran behavior. The calibration approach follows a simple fiber modeling along the interface. So this model is we defined it parsimonious because it's a very low cost model compared to the more complicated, more sophisticated nonlinear frame simulation. We also introduced some modeling of reinforcement. In particular, we consider fiber reinforced cementitious matrix for modeling, for example, reinforcement in arches structures and domes. We also considered composite reinforced mortar for modeling the spread reinforced through webs that can be glass webs in masonry buildings. And also we considered the fiber reinforced mortar for modeling the application of fiber mortar for improving the structural behavior of historical masonry structures. The discrete macro element modeling of retrofitting of this retrofitting solution can be performed through a different approach. The simplest approach is the approach based on the homogenization strategy. So according to a theoretical proposal, a homogenization strategy is considered in order to evaluate the effect of the reinforcement on the masonry macro portion. This approach has been applied in particular for masonry walls that have been reinforced according to the previously presented retrofitting strategy, and has been applied in the plane macro element and implemented in the software called 3D Macro. We validated the strategy both numerically and experimentally in several cases. Here we can see an example of this validation considering a real structures, two plane structure, two floor structures that has been retrofitted with a fiber reinforced mortar produced in Italy by a group called Armox. and these structures have been tested experimentally. So we introduced the theoretical modeling according to an homogenization approach for this kind of retrofitting and compared the results of the experimental test using the software 3D macro according to different solutions. Here we can see a comparison between the macro element and the approach implemented in 3D macro and the experimental one. The first curve, the blue one and the dotted one, are related to the unretrofitting building. The other two comparison is still related to a comparison between experimental and numerical results according to the two different solutions of the adopted retrofitting strategies. It can be observed that although the approach is very simple, the agreement between experimental and the numerical results is very high. These are some comparison also in terms of failure collapse between the experimental test, that is the higher figure, and the simulation using the software 3D macro according to the macro element already proposed by Professor Quanto in his presentation. And it can be seen that although the representation has been done at the macro scale and according to a simplified homogenized strategy, the results are in very good agreement. In subsequent research, we specifically introduced a detailed modeling of the reinforcement according to a flat element directly applied to the macro element. In this flat element that can be seen here in these figures, there is a direct interaction between the macro element and the reinforcement according to to specific discrete interfaces, and also the structural failure of the reinforcement is included. The model has been calibrated according to constitutive law, including also degradation and the different behavior in tension and compression, and has also been calibrated according to different numerical results. Here we can see some comparison that we did on specific prototype tests in laboratory, and here we can see also the simulation of the modeling of the bone slip mechanical behavior of the reinforcement. We also did some comparison considering the different type of failure that this kind of retrofitting can exhibit, considering also the possibility to consider the concave or convex surface of the specimen. And a very good agreement we obtained in this structural modeling. Some detailed comparison have also been done considering very sophisticated model in cooperation with the Imperial College, Professor Inzulina. Here we can see an application and the comparison with the experimental of an experimental test on an arch structure that has been reinforced considering two layers in the introducts of the arch. And what is really important is that the modeling of this strategy is geometrically consistent. So since the retrofitting solution is directly modeled by a macro element, the modeling is consistent. So the effect of the retrofitting solution in the extradose and in the ictradose is properly evaluated. Also, in this case, we obtained a very good agreement with the experimental results. Another experimental validation has been also conducted in Padova by a group of Professor Zampieri and Carlo Pellegrino, and they did the test, and we just compared their test with our macro modeling approach. And also in this case, we obtained a perfect agreement with the failure mechanism, and also a very good simulation in terms of comparison between between curves reporting a strengthened solution on the Masonry arch and the strengthened solution according to different according to the different steps. And here we can see how although simplified, how our macro element approach very well simulate the experimental results, both in the unenforced configuration. Here we can see several steps of the modeling, and these steps are also being compared with the experimental results in terms of failure mechanisms, and almost a perfect agreement we obtained between the experimental and numerical model. Another modeling strategy that we proposed in our research group was the use of low impact retrofitting strategies considering ductile steel frame around the openings. This solution has the great advantage not only to improve the resistance and ductility of the overall system, but also to guide the collapse behavior versus the more dissipated any opening and any retrofitting solution. The capacity curve obtained experimentally and numerically in experimental campaign performed by Ona Vera and other authors in presence of the opening, and also the same layout considering the steel frame around the opening. As you can see, the modeling of the macro element is easy to perform because it's consistent, geometrically consistent with the real layout of the masonry, and this can be done using the plain macro element, and can't be done using the frame element approach, in which there is a geometrically inconsistent between the masonry and the wall. So this particular strategy can be performed thanks to the possibility to have a simplified approach in which the macro element is plain and is not represented by only a single beam like in the frame element. And this represents a further advantage of the use of our discrete element approach for modeling the behavior of building retrofitting by using this kind of strategy. We also did some comparison considering a benchmark that is called Via Martoglio walls, that is a wall typical of a building realized in Catania at the end of the 19th century. And regarding to this wall, we did some comparison considering the use of ductile steel frame around the openings. And we can see how the walls without any reinforcement, configuration 1, is the dotted one, and the other two configurations are related to the consideration in which in the first one, sorry, the dotted one is the wall without beam floors. The gray one is the wall without steel frame around the opening. The upper two curves are related to configuration 2 and 3 that are related to the use of steel frame, that is steel frame around the opening, considering two different steel profiles. It can be seen that the use of steel frame around the openings substantially increase the performance of the wall with respect to the walls in which only floor beams are considered. The first curve is relative to the wall without any retrofitting solution, so just unreinforced masonry wall without floor beams. This strategy has been modeled by using a 3D macro, and it's interesting to observe that the steel frame around the openings have been modeled by considering the possibility of the steel frame to exhibit inelastic behavior in order to enhance the dissipative resources in the overall building. This strategy has also been adopted in a real case in companion with a glass fiber net, so in companion with the CRM retrofitting strategy, and this has been applied in a real building school in Sicily, in Italy, in which both ductile steel frame around the opening and CRM retrofitting solution have been adopted. This hybrid solution has been modeled in the entire building. It's a large building, and this building has been seismic retrofitted following the regulation code in Italy. Here we can see the difference between the original condition of the building and the enhance of stiffness, strength, and ductility due to the adopted retrofitting solution. The model has been implemented using the software 3D macro, and both the retrofitting strategy has been directly included in the discrete macro element model. So, some summary in conclusion, some retrofitting strategy and their numerical simplified modeling have been presented and proposed. The proposed numerical approach is mainly oriented to practical application, since it requires a very low computational effort if compared to classical nonlinear FEM analysis. The model has been validated by some comparison with experimental and more sophisticated numerical results. Two main numerical approaches have been presented for considering the effect of retrofitting. One is based on the homogenization procedure, and the other is based on the direct modeling of the retrofitting solution. In the next talk, Dr. Davide Rapicavoli is going to represent some application of this numerical strategy of typical buildings of Nepal. Thank you. I leave the presentation to Dr. Rapicavoli.
Good afternoon. Okay. If you want, I can share my screen. I don't know if there are some questions before to start. Or I can start directly.
Professor Kali, please say.
Okay. I'm starting. Okay. Okay. I'm Davide Rapicavoli. Good afternoon to everybody. I will talk about some case studies, some applications of the reinforcements by means of CRM technique. The composite reinforced mortar was tested by means of Professor Gattesco and Boehm in 2021 for a masonry arch vault reinforced with the composite reinforced mortar. The strengthening systems consist of a glass fiber net that is into a mortar layer, and this is applied in the extrados or in the intrados of the vault. This structure was tested in a laboratory, obtaining by cyclic analysis the cyclic response. This structure was modeled by means of the discrete macroelement method, considering the fiber reinforced element that Professor Kallio presented before, in which mechanical properties are reported in this graph. As you can see, it's possible to simulate the inelastic cyclic behavior, taking into account also for the bonding failures at the interface between the fiber reinforcements and masonry support. And at the end, we can also recognize that the fiber reinforcement allows to simulate the horizontal hinges at the arches. Another case study that was investigated is related to a masonry wall typical of Nepal. This masonry wall was tested in the unreinforced configuration and in the reinforced configuration by means of splint and bandages. Splint and bandages that are suggested by the user manual proposed by Nepal government. This wall was studied by means of the discrete macroelement method. In particular, was developed the wall without a reinforced and with the reinforced system. The analysis was obtained by means of ISTRA software that implemented the discrete macroelement method. And
please concise your presentation.
Yes. And the comparison with the experimental results are in good agreements. The latest case study that I want to show is related to a 3-story brick masonry building that is proposed in the repair and retrofit manual for masonry structures. This building was studied in 2 configurations, one with the cement mortar and the other configuration is with mud mortar. This is the 3D view of the building. Okay, I go directly to the results in terms of eigenmodes, in which we can recognize that the building in cement has a regular behavior in the principal two directions. So for this reason, no local mechanism occurs, but a global mechanism are activating in particular in the first floor. We can recognize a rocking mechanism collapse of the front facade and back facade. In the internal wall, also shear collapse mechanism combined with the rocking mechanism occurs. The structure was investigated with a different level of shear strength. In particular, when the shear strength is higher, the last floor we have in the last floor a rocking mechanism collapse that is not which is not occurs in the when we have a lower value of the shear strength. In terms of pushover curve, we can also see that we have more ductility when the shear strength is higher than respect to the case in which we have a lower value of the shear strength. And the other condition is when the masonry building is with brick and mud mortar. In this case, the floors is modeled by means of truss elements that are allowed to connect the two faces, the facade of the buildings. In this case, we can see that the eigen analysis identify not regular behavior. We have several local eigenmodes. These local eigenmodes determine are more more exposure to local mechanism. In particular, by means of pushover analysis, we can recognize that local collapse mechanism by means of out of plane failures occurs in the facade.
We are already out of time.
Yes. I conclude. Okay. The last next development of the study is related to the brick to the masonry building reinforced by the introduction of fiber elements. This study is under construction. Is just a preliminary analysis in which we will show in the next studies that we do the importance of a good connection between the orthogonal walls. In particular, is important to guarantee good connection by stitching of the corners and of the floors of the walls when we have a different thickness of the masonry walls. This is applied by means the introduction of steel bars that simulate the connectivity between the two floors, reinforcement between the two floors. So I thank you for your attention. If there are some questions,
Dr. Davide, will please stay with us. We'll take the questions at the end.
Okay.
Okay. Thank you, Professor Kallio and Dr. Davide, Rapi Kaboli for guiding us through the advancement in numerical modeling of retrofitting masonry techniques for masonry. It's really great to see this powerful interface of 3D macro, where we can even integrate the contribution of the reinforcement, even the FRPs, and model it and see directly the effect, because this was actually very lagging when we do in popular commercial software. So a big congratulations also for the whole team of Professor Kallio, Dr. Davide, and even I think Dr. Bartolomeo Pompanto here. So continuing the theme of retrofitting, now we have Mr. Gopal Singh Vandari and Ms. Akarsa Khawas from Pulsar campus, who will share their work on sustainable retrofitting techniques for masonry structures in Nepal. Please, welcome stage.
Thank you very much, Dr. Pradhan. Talking about sustainable materials for retrofitting in Nepal. Few months ago, Dr. Bhim Kumar Dahal went to Durham University and made some connection with Dr. Bartolomeo and Dr. Stephen. They were doing some research related to sustainable materials using lime mortar with some sessile fiber in UK. And they were also interested about how can we continue this research in like seismically active zone in Nepal, and what could be the alternative solution for the sustainability, considering the locally available material, which is easily, and even also we're considering about the low cost materials. So considering as a low cost materials and sustainable techniques, we selected, going through some literature reviews, we selected as a jute fiber as viable material for sustainable retrofitting. But we are just very beginning of our research and just getting material properties for beginning, and we haven't got any conclusion right now, but we are also expecting some suggestions from distinguished experts about these topics. Okay, just we are moving out of time, so I will just go to next slide. And this is just an introduction why Nepal is seismically active. This was the presentation presented by Dr. Motra sir in any talk program, which was about post earthquake damage assessment of Jajarkot. So it's like movement of tectonic plates, Indian and Eurasian plates. So I will not be spending too much time in this. And everyone, I think in Nepal is in structural engineering is familiar about this one. Also damage in the explained by Dr. Motra sir. It was for Jajarkot earthquake, there was most building damaged was stone masonry with mud mortar. And also in Gorkha earthquake in 2015, 95% was damaged here by this unreinforced masonry structures, which was brick masonries or random rubble masonries. So also about talking about building damages, this is data from DRR portal. About 36,500 buildings were damaged. Maximum 99% was like this stone masonries or brick masonries with mud mortar. So there is these are some pictures. This is also I have taken from this slide of Dr. Motra sir. So I will not be spending time in this one. There we can see some cracks and failures, out of plane failures, in plane failures in their pictures. Okay, so talking about existing, which are already existing in Nepal, there are some heading chair walls, infill walls, bracings, or splint and bandage. This is popular in Nepal for retrofitting techniques. These are also good retrofitting techniques, but talking about sustainability and locally available materials, we need to search about something need of why do we need low cost sustainable materials. So actually this topic is about sustainability, so we need to find eco-friendly retrofitting materials, and which has a initial cost, material cost is less as compared to those fibers available in market. So to use locally available materials, preservation of this cultural heritage, and low processing cost, we have selected jute fiber as a viable material. So it's also easily available in the area like India, Bangladesh, and Nepal. As I gone through some literature, it is easily large amount of jute is produced in Tarang area, around Biratnagar areas, where there is some jute factories. So we have selected jute fiber among various options. Why it is sustainable for why we selected this one. And there are some studies about mechanical properties of jute fiber as well. So it has more than average performance among various fibers, considering this mechanical and physical properties. That's why we are trying to use it as a viable material. So these are the study. How will you perform our studies? First of all, we are testing some bricks from old demolished buildings. Actually, we are talking about retrofitting that. So the buildings, most of building must be old. So we are testing material, mechanical properties and some physical properties of buildings which were damaged in 2015 earthquake. And we are getting right now, we are almost done getting mechanical properties of this bricks without mortar, without jute fiber mortar. Next is we'll be testing some mechanical properties of this jute fiber. Then we'll prepare jute fiber with jute fiber mortar and apply to the same type of specimen and test. We'll test again. Then after we getting all this mechanical and physical properties, there will be numerical modeling. For numerical modeling, Dr. Patik and Dr. Bartholomew will be helping us about macro modeling and micro modeling. So we are very thankful to them. These are the testing arrangement. How will we get initial result and final results? So the first one is for mortar beam for 3-point bending test. Second one is 7 brick assembly for 4-point bending test. And third one is single brick one for 3-point bending test. This is how we'll get out of plane properties of these brick prisms. And next one for shear strength. Actually, when we use bricks in a wall, there is a certain kind of confinements from neighboring bricks. It is never free to move. So our idea is to apply some horizontal pressure. So we have tested shear strength of bricks with 0 horizontal force with 0.1, 0.2, and 0.3 MPa. We wanted to increase this horizontal pressure, but after 0.13, there was some crossing of bricks. So we stopped at 0.3 horizontal pressure. And how will you prepare this mortar with fiber? It's like from going through some research and papers, the maximum optimum performance was obtained like 2% by weight of dry mortar materials. So we will be adding 2% by weight to make this mortar specimen, and then it will be tested for what we tested before application of this mortar. And we will also be using this scrap jute fiber, which is waste, actually waste sometimes, so you can break or some from remaining from the test. We can use up to 4 mm, up to 40 mm length. We'll be trying to mix with this mortar. And also while plastering the outside, our idea is put like first 5 mm mortar with jute fiber. Then there will be mesh like like this jute fiber mesh, which is 2.5 by 2.5 centimeter. We'll apply it up outside the 5 mm plaster. Then after that, we'll apply 10 mm of outer layer. So this assembly will be again tested for same test as this outer plane, in plane, and compression. So we'll get these results, and finally these results and will be validated by some numerical modelings. About application, we think like for multi-story or more than 2-story, we doubt it. The jute fiber will perform that insignificantly. So the application area must be like single-story masonry buildings, like this test roof buildings, and some similar kind of buildings with low cost. It will be low cost for the owner as well as for government, if government wants to retrofit these type of buildings with jute fiber mortar and jute fiber mesh. This is our idea about how will we do our research about this one. And next part is our experimental part and some data. Ms. Akash Khawas will be explaining this. I will hand over this mic to Ms. Oscar. Thank you.
Okay. Thank you, Gopal sir. Good evening, everyone. Again, I'm Akash Khawas, and I'll be presenting the results of our research work till now that we've performed till now. For starting with the brick mortar characterization, the brick samples were collected from a demolished masonry buildings from Kamal Binayak, Bhaktapur area. The two buildings were demolished, were damaged in the Gorkha earthquake 2015, and they were being demolished. So we collected those samples, brick samples from those two buildings. The main reason of collecting brick samples from a demolished building was because our main objective is to find a sustainable retrofitting technique, and retrofitting is done to existing buildings. So I think we thought that it's important for us to know the characteristics of the existing brick masonry building. So that's why we selected a demolished building instead of getting newer brick samples from the factory. The average dimension of the brick was 230 by 140 by 55 mm. Like I've already mentioned, it is very important for us to select the type of brick, and I've already mentioned the reason why we have selected the demolished buildings. We've performed 3 tests on the brick samples. One is compressive strength test in horizontal and in vertical directions, and then we've performed a 3-point bending test to determine the flexure strength of the brick, and the results are given and shown in the slide. Compressive strength in horizontal was found to be 6.52 megapascal, in vertical direction 7.8 megapascal, and flexure strength was found to be 1.81 megapascal. Gopal sir have already shown you the schematic diagram of the 3-point test. So I'll just move on to the next results. Next we tested the mud mortar cubes and cement mortar cubes. In context of Nepal, mud mortar and cement mortar are the type of mortars that are used frequently. So we decided to do test on both mud mortar and cement mortar. The compressive strength for mud mortar cubes were found to be 1.769 megapascal, and for cement mortar it was found to be 22.584 megapascal. You can see the stress strain graph for mud mortar cube. Next, we performed a 3-point bending test of the mortar beams for both cement and mud mortar to determine the flexure strength. So you can see the set up for the testing of the mortar beams, and on your right side you can see the failed sample. Next, you can see in the slide how the failure mode of the mortar beams were. You can really see that the main crack are seen in the mid span of the mortar beams with brittle mode of failure. The flexure strength was found to be 0.889 megapascal for mud mortar, and I think that's 5.55 megapascal for cement mortar beams. Moving on, these are the load displacement plot for the cement mortar beam and mud mortar beam. Next, we performed a test on brick triplet samples, both for cement mortar joints and mud mortar joints. You can see the setup for brick triplets. These tests were performed in the Central Material Testing Lab of Pulcher campus. The compressive strength was found to be 3.5 megapascal for cement mortar and 2.15 megapascal for mud mortar. This is the stress strain plot for cement mortar brick triplet. Moving on to the determination of shear strength of brick mortar joint. Shear strength plays a very important role parameter to determine the strength of a masonry structure. Shear strength generally acts in combination with compression caused by the self weight and floor loads. So for this test, for this test, we have not just tested the shear strength, but we have also applied pre-compression. So in horizontal direction, you can see the schematic diagram. In the horizontal direction, we have applied pre-compression in 4 levels of pre-compression, that is 0, 0.1, 0.2, and 0.3 megapascal using a hydraulic jack. And in first, we'll apply the pre-compression load, and then the vertical shearing load will be applied by the UTM machine. So this is a schematic diagram. I'll show you the test setup. So this is the test setup which has been particularly and specifically made for monotonic shear test of the triplets. This was made, designed and made with the help of Dr. Pratik Kumar Dheer, and we have fabricated in the workshop. So you can see the components of the shear frame. There on your right side, you can see the hydraulic jack and dial gauze to measure the pre-compression load. Then you have the triplet specimen, which is in between, sandwiched in between the steel plates. On the other figure, you can see that the triplet sample is supported on roller supports. So initially we'll just apply pre-compression load manually using the hydraulic jack, and once the required or the selected pre-compression level is fixed, then we'll apply the vertical load by the UTM machine. So the vertical load is applied by the UTM machine in the central brick of the triplet, while the other 2 bricks will be held on the roller support. So I think you can clearly see that in the diagram. So this is the setup, how it was set up in the lab. Next, just can you click on the... So we have a video of the test that we've performed in the lab. So this is the test setup before testing and after testing. These are the samples after the testing. So you can clearly see that the failure has occurred at the brick mortar joint interface. So generally in according to previous studies, in monotonic shear test of the triplets, there could be failure of the brick mortar joint, or it could fail by the crushing of the brick itself. So it depends on the level of pre-compression. At lower levels, the brick mortar joint interface is going to fail. There will be slippage of the brick mortar joint interface, whereas as you increase the pre-compression level, the brick blocks itself could fail by crushing. These table shows the data that we have obtained from the experiments for 4 levels of pre-compression, 0, 0.1, 0.2, and 0.3, and we have plotted the graph. You can see the relationship between the shear strength and pre-compression. As the pre-compression level increases, you can see on the x-axis that is pre-compression level. So as pre-compression level increases, the shear strength is also increasing in our case. So from this graph, you can calculate the cohesion and the friction angle. So moving on, these are the tests that we have performed in the lab. The remaining works that need to be performed, like Gopal sir have already mentioned, we still need to make more samples with including the retrofitting part. Like we need to prepare the wire, jute wire mesh, and plaster the wire like he had already given that schematic diagram shown you. So after those tests are performed, we'll also be performing numerical simulation. The main objective of the microscale modeling is to visualize the locations of the critical internal stresses and strain developed, and to simulate the experimentally obtained progressive crack or failure developed in the masonry triplets. So this is after we perform the tests on the samples which are retrofitted with jute fiber mesh. These are the future works I've already mentioned. We need to determine the mechanical properties of the jute fibers. We need to prepare the brick triplet and 7-brick prism with jute fiber mortar, and need to perform the experiment test and numerical modelings. Thank you. Before taking a leave, I would like to thank Dr. Bartolomeo, Dr. Stephen, Dr. Pratik D from Durham University for giving us this opportunity. Also would like to thank Dr. Rajan Swal from Pulcho campus. Would also lastly would like to acknowledge the civil department of Pulcho campus and the staff of Central Metal Testing Lab of Pulcho campus for supporting us in this research work. And also would like to mention Mr. Prashish Narayan Sapkota, who's also an integral part of our research work, for his effort and time. Thank you very much, everyone.
Thank you, Mr. Gopal and Ms. Akarsa for showing us what we are really doing here, different tastes in our own institution to make our masonry sustainable, more durable. So it's now time for a short break. I hope we can make it little short, then planned. Let's take it for 10 minutes. I think it will be okay because we are already overrun the time by 10 minutes, not much, but we want to be in the schedule and we'd like to continue with our interesting works ahead with Dr. Pratik. See you very soon. 10 minutes, please.
Structures in Bhaktapur area. So we can see the picture one is like we can see the out of shear failure. Then we can see some vertical joint failure. Then in the third picture you can see this out of lane failure, which is supported by a steel pipe. This may be a temporary solution, as we can see. And we could identify some. You can see in the figure one, it's like a window shade with there is no reinforcement. It's just a brick and mortar together. And in the right hand side picture number 3, you can see this is like a new construction over an old building. So we realized during our site visit that we try to identify some critical point on which we need to move further. So we found that the weakest connections between this wall and corner can be really vulnerable. And definitely we need to better characterize this in-plane, along with the in-plane studies, we need to focus on outer-plane study and sometimes combine in-plane and outer-plane studies because for that, because when we do go, let's say we are working on Abacus or any detailed modeling approach, in-plane may be quite easy, but when we need to study the combined in-plane and outer-plane action, it may be computationally so expensive. So we had to make a balance between the computational time and the efficiency. So yeah, so this is, you can see this is in Lalitpur, like in Patandarbar, I think we have identified some like temporary solution, but when there is a like small earthquake can lead to like major destructions. Yeah, so then the idea is to strengthen the masonry, like unreinforced masonry structure. So there are like many popular techniques that are available, like fiber reinforcement, polymer, textile reinforcement mortar, then engineering cementitious composite, then fiber reinforced cementitious matrix. Then most popular is one this splint and bandage method, which is quite popular in Nepal. But then talking about the limitations, when you're trying to strengthen the like wall, so we may add some extra stiffness to the system, and sometimes it may be it may be really costly to implement. And now we need to be worried about whether this is sustainable or not. So then I will come up all this discussion on the sustainability. Yes, so So what we try to do, we try to do some characterization test on Durham University in our civil engineering lab. So we identified some like locally available brick type. We did some compression test, a simple compression test just to characterize this like compressive strength. Then we did some 3-point bending test to study the flexural behavior. Then instead of, so we are trying to, we are avoiding the use of cement mortar. So that's why we have selected lime mortar, and we have considered 2 grades of mortar. One is NHL 5 and one is LFS 3.5. So NHL 5 we are using for building the specimen, because this is the intermediate mortar, the joint for the joints. And we are using like NHL 3.5 for the render, or we call it plaster in India as well. There are a few limitations with the lime mortar, definitely, because this cannot match up to the strength and performance of the cementitious mortar. So there has to be some enhancement and improvement we need to provide for the lime mortar if you are going towards the goal, to achieve the goal of the sustainability. And coming to the so then we try to investigate all the possible ways how we can enhance the render properties. So there are a lot of literature available on different kind of fibers we add to the mortar to enhance the properties. Definitely the steel, aluminum, carbon, and glass fiber, they provide really high tensile strength, and they provide really good performance. But then when we discuss, but we are trying to go with some natural alternatives. So like when we try to investigate the alternatives, so we found many good options like hemp fiber, jute fiber, and sisal fiber. And it's not about choosing the fiber, it's about the overall cost. Because let's say in my country, I don't have a good production of, let's say in India or Nepal, it's much easier to go with the jute fiber. But if it is in if it is China or maybe it's Brazil, then they may go with the sisal fiber. So we have to make a balance and between what fiber we're trying to investigate in our research. So so there are different advantages and disadvantages that we can outline for the natural fibers. Definitely, it's like environment friendly. This is and this is there's low emission, low cost in manufacturing. But talking about the drawback, which is really we need to be worried about. This is high, we have high water absorption because these are organic materials. Then we have low durability. Then we have low strength as compared to the synthetic fiber. As compared to the plastic fiber or this polymers, they are not that durable. And then there is no much standards available to characterize all this material behavior. And lastly, the thermal stability is also not that good. So that's why we try. So in our research, we are trying to. We started with sisal fiber. So this was just because just to make a balance between the availability cost and all this material strength properties. So, but when we were trying to do a literature study, so we realized that they always recommend to do the characterization test with some treatment of this because this treatment is like fiber surface treatment. We can say if you see this number 4 and number 5, so they're trying to treat the fiber with a chemical solution, and most popular solutions are like calcium hydroxide and sodium hydroxide. The idea is because if you see the graph in the bottom corner, so it doesn't increase or enhance the tensile strength a lot, but the benefit is it allow the progressive slippage, then uniform distribution of the stresses among the fiber, and definitely this improve the durability. Because as a structural engineer, we expect the structure to damage. We expect a controlled damage, not a uncontrolled damage. So this is the idea is to, because if you see this blue lines, they are like treated fibers, and you can see quite linear. But if you see this untreated one, there's green one, they are not so regular. So this is the enhancement we get when you do the treatment. So so we started some characterization of this cube motor beams. And if you see this number 4, 5, and 6 combination, so we have NHL5 motor without any fiber. Then we have render without any fiber. Then we have added the fiber in that NHL 3.5 like not yeah. So then we try to do some material test on the compression. So if you can see, so this is the stage 1. When you apply the load, we can see the it started fail. So if the failure is like in 1 millimeter, 2 millimeter, we get the complete failure. Then you can see this inverted prism shape, which is quite traditional when you do the testing. This is the like cube we have tested. This is with added fiber, and I think if I might have missed to add, like we are using 40 millimeter fiber length fiber, but I will discuss what are the parametric study we are going to do after that. So yeah, so actually we are going to do some detailed numerical modeling, but this is just a visual. I just added just to show. This is for the traditional render. Yeah. So then we try to do some flexural test for the motor beams with and without fiber. You can see this. If you see this, so if it doesn't. When there is an applied load, if you see from the graph, you can see the orange one is without fiber, so it goes on, and at some level it just like break and it cannot take any further load. But this is with the fiber we have it's more gradual, so it has better tensile strength, lower stiffness, which is is quite beneficial for us. Then thirdly, it's more gradual. It's not sudden, so we have enough time to predict the failure. And then we also try to characterize this shear strength properties. We have prepared the triplet. We could only test for the like compression, but because it's still ongoing. It's only been 3 months, so we are still in the stage of testing. So this is the specimens we have prepared. We managed to do at least one test for each type. So if you can see the figure 1, so this is without any render. The number 2 is with render, but no added fiber. And the third case is like a render with added fiber, and that is 40 millimeter. So if you can see the failures, if when it cracks from the joint, it has a complete failure. And here, like even though it fails, but still this fiber try to hold it together. And if you can see from the graph, so this the blue one is without any render, and this orange one is with render, no fiber. You can see we got definitely higher stiffness, but this peak is not high enough as compared to the fibrous render. And this you can see this is more like a gradual. It's not sudden. It's more like gradual. So this helps So then we are trying to do some like we also managed to do compression test just to predict the capacity, which is almost 6 MPa we got for the masonry. And definitely we are still in like a developing stage in the shear test, and we are expecting to do this next week. Yes, so yes, as I said, we are doing the shear test, and yes, so there are like many literatures. They have identified what may be the material parameter chemicals that may improve the fiber durability. So definitely we need to do some parametric study on different type of chemicals available because they differ. Like for example, some chemicals we have lesser curing time. But lower like efficiency, and somewhere we have like a higher curing period and a higher efficiency. So we have to make a balance what exactly we need, because time is also a big parameter. And fiber length, because this we identified when you try to work with 40 millimeter, because 40 millimeter can be the maximum in our case, because when you have a longer like a fiber length, it may increase the tensile and compressive strength, but it is like quite difficult to work with. So when you prepare the mix, it's really difficult to to mix everything together. So we're trying to make a balance between the workability and the mechanical parameter strength. So it's like 10, 20, 40. These are 3 combinations we're trying to identify. And then fiber percentage also plays a major role, because if we it's not like that we'll add a lot of fiber and it will work. So it will definitely affect the like performance, mechanical parameter. then we need to also understand how the thickness of the render or plaster is going to influence the overall performance of the system. Yeah, this the idea of like doing this experimental test is to get all the material parameter needed. Let's say this flexural test of wall will give us the how we can correctly optimize our out of plane behavior. Then shear test will give us how to get like identify this shear strength parameter so that we can correctly identify this interaction properties for the joints. So yeah, so there can be, because in our case where so we can go with mesoscale modeling, microscale modeling, and microscale modeling. When there is a small triplet or small specimen, we can go with microscale. But when there is a wall or full building or full big structure, we cannot go with micro or even meso because this will be computationally so expensive. Like I'm talking about abacus or any like finite element modeling approach, but macro model can be quite computationally expensive. So this is so we are trying to like investigate all modeling approach so that we can validate. Dr. Davide also is working on this simplified approach, and we're trying to make a balance between computational time and accuracy. So this is the case study we're trying to identify. This is a case where they have tested in UK. So this is like they have added some rebars. And they're trying to add a 60 millimeter of render on top of that. So yeah, so like so what I'm trying to do, so here I can just come back to, yeah, so sorry. Yeah, so like if I'll just like I'll go back to the previous slide. So here what I try to do, so we have this wall, we have the render, and we have the rebar. So we are trying to integrate everything together. If you can see, this rebar is integrated within the render, and then the this render is like connected with the wall with an interaction. So we have a few parameters. Sorry. Yeah, so like we have identified all the material parameter that has been already available in the literature for brick, mortar, and render. Then we have to because if we are using a homogenized model for this one, so there is no interface element for now because we are avoiding mesoscale modeling just to improve some computational time. So sorry, yeah. So these are the parameter for the material parameter. You can see for the rebar as well, and these are some interface parameter because in between like a render and wall we have some interactions, and we have calibrated, and we found some optimal parameter. Then we try to compare with the experimental response, and these are developed. You can see the number 3 and number 4. These are that unreinforced masonry building that has been compared. You can see the we are almost having some similar response. Maybe some mesh refinement can improve some more result, but it will increase the computational time. So I try to make a balance between everything. So if you see the right side, number 5 and sorry, I think there is a mistake. Number 5 and number 6, we can say. So there are some micro cracks. We could not get the really fine bands, but at least we could identify some major cracks. You can see some green lines here and here. So here you can see how this unreinforced and reinforced system behaves. So this left one animation is for the unreinforced masonry. If I go to the right one, so here if you can, in the left one, you can see there is a diagonal, like crack formation, and here it is more like a sliding. And we can see, and if you can see the top, I try to show differently how this deform looks in the wall and in the render, and this is the combinations. Yes, so we are trying to, I think Dr. David is trying to help me with comparing all the responses. So he's working with Histra. So we're trying to compare how our results are, comparable. So yes, towards the conclusion, definitely we're trying to develop some low-cost solution that can be applicable in the developing countries as well as developed countries. And we are trying to get our, get a good balance between the optimal mixing of the fiber in the lime so that like we can commercialize it. And we are still in a discussion with one of the lime production company, and they are trying to help us to share their industry experience, and we are trying to develop some collaborations. And definitely we are trying to focus on developing a natural and low emission material, then optimize structural scheme also. This is one of our goal that we want to achieve. Then definitely computationally efficient model which can predict both in plane, out of plane, and combined in plane, out of plane behavior. And finally developing some technical guidelines and helping the building standard to revise. And yeah, definitely we want to try to establish our partnership with Nepal, and this will help to prepare and for like new proposals under the PSA SRC scheme. I think that's it. With this, I will conclude my presentation. Maybe we can directly go to the discussion round. I have a couple of questions from the from the online chat. Yeah, so we can organize. Yeah,
Dr. Pratik, I think I will pass the online comments after finishing here questions.
Yes, I have already added them in the slide, so maybe it's easier for everyone. Maybe if one question is for Dr. Rajan and one is for Pando, if you can see my slide, if that helps.
Okay, that can be done. Yes, please.
Okay. Or else we can start with the offline, whichever you like. I'm okay.
No, I mean, if we have already said, then please.
Yes. Okay. Dr. Rajan, there is a question for you. If you can see my screen.
Yes, Dr. Pratik, I am listening.
Yes. Like, can you see my screen in the?
Yes.
Yes, I think there is. Yeah, there is a question like, could you please tell about the failure conditions of foundations of masonry structure that can be observed during Gorkha earthquake?
Failure condition.
Pratik is really not visible.
Is that okay? Okay.
Can you
yeah, I can read out. Okay, I didn't. Okay. So I think there is a question from Ramchandra Bharti, and he's asking, could you please tell us about failure conditions of foundations of masonry structures that was observed during Gorkha earthquake?
Generally, it is not visible in the foundations because it is difficult to see there. But we have seen in certain buildings, in the masonry buildings, due to the vertical shear, there is an unequal settlement. And when there is an unequal settlement, and it is found vertical crack. That is the one thing. And another thing, we have seen the certain buildings nearby the Bhaktapur in the Biashi. It is northern part of the Bhaktapur, where soil property is very weak. And we found the tilting condition of the masonry building. And there is a certain tilt around 4 inch, that means 100 millimeter. And we found another one buildings nearby that is again in the Bhaktapur, and that is mainly in the field area. And there due to the little failure of the foundation, but in the masonry building, whatever we observed, not a lot of problem in the foundations, mainly problem in the outer plane and in plane and shear. And we found the most of the masonry buildings out of plane failure. This is because of the connection between the main wall and transverse walls are not properly, and they are not properly connected. That is the one thing. And another things, and there is no timber and other bands between that. That is the second thing. Another things, in most of the masonry buildings, we have seen that from top to the bottom, and the main wall and transverse walls are separated. This is because of the not connected properly by the element. This is the cause. And the transverse and the shorter walls are fail
due to the slenderness ratio. That's why from the side of the foundation, we found the very little, means 5 to 10% solely, and main failures are out of plane and gable failure and the shear failure. I think I answered the question.
Yeah, okay. I think thank you. Yeah, I think it should be helpful. Yeah. Yeah, okay. Can we go for the second question, or anyone in the have a question for me, or even for?
I will raise the question for you later.
Yes,
if there
yes,
are
please,
any
yeah.
questions online, so please continue.
For now, I only got 2 questions from the chat. But if you have any question for myself, then I'm happy to tell. Yeah.
Okay, I think
there are Pratik question
Yes.
for me as well.
Yes,
If you can
one question is for you. It's a bit it's a lengthy one, but I can read out if you it's okay. So maybe there is someone I'm just trying to add him in the group.
Please, if you can read, I'm not
Yes,
able
yes. Okay, okay, just a second.
Or probably if you can get bigger your screen.
Yes. Yeah, but yeah. Can you see, or I'll just read it out? Yeah, I think I can just, it's better to read. Yeah. So this, he has a query regarding energy dissipation system of masonry walls. So talking about this energy-based design in RC framed building with modeling of infill masonry wall, we knew that due to different stiffness properties in infill masonry wall and RC elements, majority of the dissipated energy is through infill wall. Underestimating this RC structural elements like beams and columns, due to which real energy dissipation is not achieved in the structure. So how to eliminate this problem?
Yeah, so this question is like a very interesting question. We didn't touch this issue through this workshop, but actually, in addition to unreinforced masonry buildings, we can have mixed structures, including infill frames or confined masonries, in which infill walls, masonry walls interact with frames, reinforced concrete frames. It is true that in this kind of buildings, a lot of energy is dissipated by the cyclic behavior of masonry. And something, when we saw the cyclic behavior of this morning, when I showed the cyclic behaviors of the panels failed by flexural and shear, diagonal shear, we saw that in the case where the failure was in shear, was in diagonal shear, there the masonry was dissipated a lot. So what happened in infill frames is that the only failure mechanisms that can be activated is in shear, because the flexural one is avoided by the confinement effect of the reinforced concrete or steel, whatever frame. So it is true that the role of masonry in that case is in the dissipation, dissipating energy. If we want to simulate this aspect, what we can do is, of course, modeling both part of the structure. We need to model explicitly the reinforced concrete frame and the masonry, and most importantly, we need to model the interaction between the two parts, the two materials, which is itself non-linear. And again, if we want to have an idea about the dissipation, the energy dissipation, in principle, we need to perform at least a cyclic analysis. Through a pushover analysis, we cannot estimate.
Yes. I think there is another follow-up question from the same person. So this is regarding another queries related to masonry, like infill masonry wall and frame element interaction. I think it's the which we have already answered, I guess. What technique to be incorporated the connection modeling in the infill masonry wall to avoid damage in the frame, like frames in the interface? Yeah.
Exactly.
Yeah.
Let me conclude and including an additional information before, and then
Yes,
we
yes.
can discuss about the interaction. So, in addition to the energy dissipation, in the case in which we have this sort of interaction between masonry and the frames, another aspect that can or should be considered is the changing of the dynamic properties of the structure,
Yes.
if we consider or not the infill panels, the infill masonry panels. Basically, what happens if we model only the masonry or only the reinforced concrete frame, and we do any analysis, perform any analysis, the modes of vibrations and the lateral stiffness, whatever, is completely different compared with the system interacting together. So this is very important in this case, modeling both systems.
Yes.
And then we come to the second question: how can we model this interaction? So we didn't provide, unfortunately, we didn't provide any information through this workshop. However, some techniques, including a particular version of the discrete macro element model, have been adapted for simulating mixed structures. In this case, the interface elements that we saw this morning be used to simulate the interaction between the two panels. Using a similar approach, these elements are used to simulate the interaction between the masonry and the surface of the reinforced concrete frame. In this case, what we can do is to simulate the crushing or the detachment of the frame, many times observed closer to the corner of the element, and also we can include the damage within masonry and the frame as well. So to answer the second question is regarding the discrete macro element model, the approach is almost the same, using links connecting both connecting the masonry with the frames. Of course, some numerical problems or ways to try to optimize or to make the model robust then come and make the problem a little bit complex from the numerical side, but in principle is very similar what we discussed about this morning.
Yes, yes, I agree. Yeah.
This is a very important. So visiting also many parts of the Kathmandu, we saw a lot of reinforced concrete structures. We have also in Europe many of these. Unfortunately, many times these buildings are designed or assessed just neglecting the influence of the infills. And this is sometimes the results that we get are very unrealistic. So these two questions have been very important to at least to highlight this problem that we couldn't face this in this workshop properly, but hopefully in the future we'll have time and occasion to speak about.
Thank you, Walter. Yeah, for your
answer. There are other questions?
From the chart, I can see this is the two questions I have received, and I don't see any further for now. No, I think, yeah, we don't have any questions for now, but maybe you can have some questions from
maybe Dr. Pratik, maybe we can continue with the online questions later. Let us handle the questions physically here first.
Yes, please.
Well, I have received some questions already. I would like to start with Dr. Bharat Mandal sir here. He has some questions for, I think, all our presenters. Sir, please put your questions